Okay, this was an example of the things that I'm expecting you to be able to do for the class. And what we do is we're going to begin with a differential equation, which is right here. This is obviously in Mathematica. So this is your differential equation. Given a differential equation, I'm expecting you to be able to identify the output variables, the parameters, and the input. In this particular case, the output is the variable that is being solved for from the differential equation, which happens to be x. So here x is the output variable. The input is the force. So typically you will know what the force is and then solve the differential equation for the output. One of the things that I would expect you to do is to put this equation into standard form. So a second order equation with standard form is given in this one, which is fairly simple. What you want to do is make sure that you match up all of the parameters in each equation. So in the second equation, there in front of the x double derivative, there's a 1. To make the first equation look that way, you have to divide through by mass. So basically take the first equation and divide by mass. And then match up the terms. So this term is in front of the x, and so that's what this term is. So w squared is equal to k over m. It's usually called omega. It's a frequency. And then the second term is it's usually zeta. I write it as z because it's more convenient in Mathematica. So this will cause them to match up. And on an exam, I would expect you to be able to go from, if you know k and m, you can get w and z. If you know w and c, you can get k and c. If you know w and z, you can get the k and the c, and vice versa, in whatever combination. So if you know 2 of them, you can get the other 2. I would expect that. I also expect you to be able to take your differential equation and find the s equation for it. And so here's the s equation for this differential equation. And I expect you to be able to do that fairly quickly. I've shown you how to do that in class, and I'm going to belabor the point here. Now what I'm going to do is try to demonstrate some of the solutions to this. I'm going to solve the differential equation, and I'm going to solve the s equation. I'm going to point at solutions in the s equation and try to convince you that you can look at the s solutions and identify what the differential equation is going to do. First thing I'm going to do is put the input force as 0, and this is called free motion because there's nothing that's forcing it to move. So this is going to be free motion when you do this. And then of course what I'm doing is solving the s equation, and then I'm going to solve the differential equation, and I'm doing it 2 ways. I'm simplifying it and then doing a full simplify. I'm going to demonstrate that those 2 are the same, even though one looks perhaps more understandable than the other. In this particular case, I'm starting off with initial condition, initial velocity. So these are the solutions. I'm not expecting you to do those, but that's the solutions. Now what I'm going to do is I'm going to pick some numbers and then do some plots. So for the first one, I'm going to let w be 2 pi. I'm going to let z equal 0. This is equivalent to having damping equal 0. So there's no damping, no damper on there. You can probably imagine what this thing's going to look like in the solution, and obviously you can see the plot right there. If it has an initial velocity with no damping, the damper is what's taking energy away. if you're not taking any energy away, you wouldn't expect it to stop. And in fact, that's what happens here. So you take these numbers and you plug into your answers, and here's what you have. Here is the solution of the S equation if you use the numbers that I've chosen. And I've pretty much chosen these, kind of plucked them out of the sky. So anyway, if you notice, the S equation has two imaginary solutions. Two because it's quadratic, so you're expecting two. They're imaginary. The imaginary number always comes in pairs. So if you notice here, one is a plus, or one's a minus, and one's a plus. They'll always come in pairs like that. If they don't, then you've done something wrong. And the value is 2 pi. Okay, so what's going to happen is in the S equation, you're going to, in general, have real parts. You've seen that before, and you may have some imaginary parts. What this means is that the solution for x, if you solve the differential equation, it's going to have some stuff, maybe some initial conditions and whatnot, and then there will be an e to the real part times time, and then that will be multiplied by maybe some constants that depend on initial conditions. There will be a sine of the imaginary part times time, plus or minus, and then maybe some more numbers because of initial condition, and then there will be a cosine of the imaginary part times time. So that's the general what this S term means. So let's look at the solution. There is no real part, so this piece right here is e to the 0 real part times time. E to the 0 times t is e to the 0. E to the 0 is 1. And so what happens is what's left over here is multiplied by 1. The 1 is not getting smaller. The 1 is not getting bigger. We call that marginally stable. And what that means is it's not getting bigger, but it's not going to get smaller either. Okay, so, and if you look at the solution to the differential equation, you have it right here. This is probably the easiest one here. So if you notice, this matches the form that I'm trying to indicate to you here. X is going to be e to the 0t, which is 1, times the sine. Could have a cosine, but because of the initial conditions here, it just happens to have a sine. But the point is, it has some sines and maybe some cosines in the solution. The other thing to notice is that it does match up. The imaginary term is 2 pi, right here, 2 pi, and that shows up right there in the sign, 2 pi. This guy right here in the denominator is part of the initial condition. That just depends on how much you pushed it when you got it started. But the point is that it has a sign. So here are some of the questions I would ask you. I would ask, is this stable? The answer is no, it's not stable. It is marginally stable. How do you know? Because if you look at the real parts up here, there are none. It's not positive, it's not negative, it's 0, which means it won't disappear. The next thing would be time constant. In this case, it is never getting to where it's going. You can see that in the plot. It never gets there, right? It just keeps oscillating forever. And so the time constant is infinity, or doesn't exist. And you look at that because of the real parts of the S equation. The other thing I might ask is, does it want to oscillate? Yes, it does. How do you know? Because it has some imaginary terms on the S, which means that it will have some sines and cosines in the solution. So it has a desire to oscillate. You can see that it is. So those are the kinds of information I'm going to ask you in the S equation. And then here are the two plots. I'm just trying to show that that these two equations, this one and this one, are identical. So I've just plotted those two things, to show you that they're the same, even though they look weird. Okay, so the next one I'm going to do, same omega. By the way, let me point this out. If you look at the frequency of this sine wave, when does the sine repeat? It begins right here at 0. Doesn't always, but because of the initial conditions, I'm just trying to keep it as simple as possible. So it begins here, and it finishes the cycle, one cycle, right here at the time when it completes the cycle is 1. The sine wave repeats, the sine and the cosine repeats at 360 degrees. Every 360 degrees it repeats. 360 degrees is 2 pi radians. So the sine and cosine will repeat every 2 pi radians. And so what I have here is a sine, and the number is 2 pi times time. That's the solution. So this thing will repeat whenever this thing goes every 2 pi. So what time will that be? 2 pi times t equals, when is it 2 pi? It's pretty obvious. Time is 1. Okay? So what this means is this guy right here will repeat when the time is equal to 1 second. And that's what you see up here. It's repeating when the time becomes 1 second. So what this means is this imaginary number that is right here, that came from the S equation, this guy right here is the frequency. It's called the frequency of the solution. And basically what it does is it tells you how quickly the sine wave is going to repeat. So the imaginary term is the frequency. Okay. So taking what we've learned from that one, let's do another one. Here again I'm picking two numbers. This guy is the frequency. And it's going to be the same as before. Frequency is going to be 2 pi radians. Radians per second. On a test, I would expect you to be able to convert that to degrees per second, cycles per second, cycles per minute, revolutions per minute, all of those things. So for example, if it's 2 pi, if the frequency is 2 pi radians per second, and you want to convert to RPM, then you want to do a unit conversion. So there are 1 revolution in 2 pi radians, and there is 60 seconds in a minute. And so you cancel the seconds, you cancel the radians, and you're left with revolutions per minute. So it would be 2 pi divided by 2 pi times 60. So this would be 60 RPM. Be able to convert back and forth between units on that. This time I'm going to give it some damping. The Z is called the damping ratio. So now it has some damping. If the Z, it's actually zeta, but it looks like a Z. If zeta is less than 1, we call this underdamped. Underdamped. Okay, so if you put those numbers in, solve the S equation, this is what you get here. Okay, so let me ask the typical questions that I might ask. Is it stable? How do you know? You look at the real part, and that is the exponent term in the differential equation solution. So there will be a term that looks like this, minus pi times time. And if you look at the solutions, the fully simplified one, the term is right there. And then if you multiply this one out, this one here is a little bit weird. So this time it's not as convenient to look at this one. But if you multiply them out, you can see that this guy has essentially the same thing as this fully simplified one. So the point is, you can look at the S equation, see that real part, and then you can make the prediction that it's going to have an E term with that real part t. Okay, so is it stable? Yes. Why? Because the real part happens to have a negative number. And so here, E, in the solution, you have e to the negative number t, which means that as time gets bigger, this term that's circled here, this term, will get smaller and smaller. So yes, this guy is stable. You get that from the real part. Does it want to oscillate? Yes, it does. Why? Because it has an imaginary term. And if you notice what happens, that imaginary term becomes, in this case it happens to be just a sine, but depending on the initial conditions, it could also have a cosine term in there. So the point I'm trying to make is, if it has an imaginary term, there will be sines and cosines in there. And so yes, it will tend to want to oscillate. What is this number in the denominator? It depends on the initial conditions. So those are those constants that are in there. We don't know much about those using the S equation. Most of the time you don't really care. And so here's the plot. I've made the two plots like before just to show you that the simplified and the fully simplified are the same. And you can see that it has this tendency to want to oscillate. It is, however, dropping off significantly because of the exponent term. And so it's damped. It's coming back into zero. It's not being forced, and so when it settles down at zero, which is kind of what I think you'd expect. If you had a spring and a damper and you pushed on it, to get it started, it would eventually, the energy would leave and it would stop moving. So yes, it's stable. It does want to oscillate. It's difficult to see the frequency of oscillation on this graph because it doesn't repeat enough to where you can catch it with your eyeball. But the frequency is given by the S equation, the solution to it. Frequency is square root of 3 times pi, and this will always be radians per second. That comes off the S equation. You can convert that if you want to RPM or whatever. The time constant usually is written as tau. The time constant is basically taking the component of the E term minus pi t, setting it equal to a -1 and solving for the time constant. So the time is equal to 1 over pi. The easier thing to do is you say, okay, the time constant is, you take the real part, you change the plus and minus sign, so it becomes positive in this case, and then you take 1 over that value. So the time constant, looking at the S equation, is 1 over pi, which is what I'm calculating officially here. So that's the time constant. The settling time, when does it arrive at within 2% of where it's going to go? And that's always equal to 4 times the time constant. So 4 times time constant, so in that case it'd be 4 over pi, which is, pi is about 3, so this is about 4/3 approximately, so about 1.3, so that would be right about here. So that's about where it gets to within 2% of where it's going. Kind of hard to see off the graph, but yeah, approximately there. Okay, so let's do another one. This time we'll keep the same frequency. Now the damping ratio is greater than 1. We call this over damped. If Z equals 1, it's called critical damp. And again, I solved the equation. Okay, this is what it looks like when it is over damped. Okay, so let's answer the questions and then we'll look at the graph. Does it want to oscillate? The answer is no, because if you look at this, these are all just real numbers. Right? You might want to pull out your calculator and determine that. So no, it does not want to oscillate. What's the time constant? Well, in this case, there are 2 of them. It's going to be, let's see if I can find it, real quick. 4 pi, 4 times pi minus 2 times the square root of 3 times pi. So one of them is, let's see, this one is, let's see, 4 pi minus 2. Okay, this one is 1.68. The other one is minus 4 pi. Let's see, messing this up. This one is a minus 1.68. The other one is a minus 4 times pi minus 2 times square root of 3 times pi. This one is a minus 23, which seems a little high to me, but let's say that those are the two values. Okay, so the thing is that you either have you have two of them, 1 over 23, or it's a 1 over 1.68. This one here is clearly the larger one. This one is very small. And so you have to decide which time constant do you return on an exam. It's this one. You always return the biggest. Whichever one it is, you pick out the biggest one. The idea is what the time constant is supposed to tell you is the length of time it's going to take until it gets about 62 some odd % of where it's headed. And it's not there, it hasn't arrived until every part of it arrives. So this one will get there quickly. This one will get there fast. The big one here, this is the one that's going to last. So to be fair, you give this as the time constant. Give the biggest one. Okay, so that's how you handle multiple values. And again, if you look, when you solve the differential equation, if you look carefully and multiply this one out, you'll discover that the two e terms are both negative, and they'll end up being a negative 23 and a negative 1.68. If you really fully simplify them, decaying exponents is essentially what the sinh term is, the sin h. The sin h does not oscillate because it only contains decaying exponents. Is it stable? Yes, it's stable. How do you know? Because all of the real parts of the S equation are negative. So it's stable. If any one of them was positive, that would mean that one term gets bigger and bigger, which we would call unstable. So it's stable. We found the time constant. It does not want to oscillate. And so if you look at the plots now, you can see that they don't oscillate. They go up and they come back down. So it never crosses the axis. It does not want to do that. You can make it, but it doesn't want to. Okay.